or Kathleen, but we will get your feedback to the students. If you have the Qualtrics evaluation survey, please jot those down in here. Hopefully you can see that the students are taking those questions and feedback seriously.
One quick note to that moving forward, we do have a plan to test the air sensors as we are going forward. I believe they're already ordered and on the way, and we do have a plan to test them in prop wake to see if they are working correctly, and if not, obviously we'll move forward with our contingencies.
Okay, all right, good. Thanks for the clarification. Again, we will shift gears here now to Team 2. So I will pass the ball to Team 2. A public service announcement is if you come on and you haven't muted your microphone, please do so unless you're going to talk.
Riley, Amber, Alex, and Enzo, are you all here?
Alex is here.
Yes, we're here if you're ready.
All right, roll. Hey everybody, my name is Jared Adams. I'm the Power and Propulsion Lead for Team 2. We are the Flying Pharmaceuticals, and we're ready to rock and roll on this. So just going over our team organization, as I said, I'm Jared Adams. Project manager is Andrew Bruce. Lead engineer is Riley Budd from BYU. And controls electronics and structures is Amber, Robert, and Caleb. And payload and aerodynamics is Michaela, Enzo, and Alex. So currently, hypertension is the leading cause of death in Haiti. It was 2,200 people that died last year, and that is increasing every year. It's the leading cause of death over many other diseases like HIV and AIDS. And currently, the method of treating this illness is through pill form, and the way that they are treating it is they're delivering the pills through a central pharmacy called Conj. And one person from the village that needs pills is walking from wherever they are over to Conj through bad infrastructure, trails, mountains, and it's a very slow and tedious process. So to combat this problem, we've identified that a UAV would be a very feasible solution to transporting the pills. As I stated earlier, this is Conj up in the right-hand corner of the picture. That's the central location, the pharmacy that receives the pills from many nonprofit organizations. And this is a sample path to Mont Michel, which is a village that needs pills. And as you can tell, it's somewhere to hike from Mont Michel over to Conj. They'd have to go around that lake, hike through all those mountains. It's just a very long process. It's over 14 miles just in a straight line. So if we were to have a UAV that were to fly at 27 miles per hour, it'd take about 15 minutes in one direction. So this is some answers that we have in response to some questions that we had on NCR. We've added a budget for our camera and video TX in our controls budget. Our range and flight ceiling, which was asked about, is a 12.4 mile range, which is above the average distance between a lot of the villages in Conj, and a 2,600 foot ceiling, which is higher than the highest mountain in Haiti. Our cruise speed, like I said earlier, is 27 miles per hour. That's found out in our aerodynamics by Enzo and Alex. And our payload capability is 2.6 pounds. And our drop height is 50 feet. And we're going to define our payload impact resistant container from that drop height of 50 feet. So to go through our mission definition, our KPIs are that we have to weigh less than 15 pounds. We have to have that flight range of 12.4 miles in order to get to all the villages efficiently with optimal amount of battery left. And payload dropped is from 50 feet, like I said, and payload lands in a 100-foot radius, preferably on a field or somewhere where we have that much room. And we have to be able to transport 7,000 hypertension treatment pills per flight, and that's defined in the amount that the average village would need on a monthly basis to last them between flights. So our stakeholders, it's really important for us to have a good interaction with them. We want to make sure that we're able to integrate very well into the Haitian villages, make sure they understand what's going on, and we want to make sure we're exposing them to technology And the Pharmacy of Conj, like I said earlier, is the one launching and housing the drone. They're our central waypoint. The community representatives are the ones that are actually receiving the packages, dispersing them, and they're going to be charging the batteries and having a lot of interaction with the drones. And the CDC is our nonprofit organization at Clemson that we're working with. They're serving as our middleman, providing us with information about Haiti and updated mission requirements that we may need to know about.
So the first problem that we needed to address as far as our payload is that the whole point of our mission is that there doesn't need to be any extra transportation between the village and Conj. So we needed to find materials that were in the pharmacy, around the pharmacy in Conj, so that they didn't have to take any extra trips to get materials. So according to the intern that we have in Haiti, cardboard, metal clothes hangers, and duct tape were going to be our three best options that we could use. So looking at the picture that's there on the right, we chose metal hangers as it was drop tested from a 4-story building using M&Ms as fake pills, and 899 out of the 900 successfully made the drop. So we have deemed that this will be our payload structure. The configuration of it was deemed based on the lowest cross section that will go into our fuselage to decrease drag. So now we've moved into how we're going to deploy it from the aircraft. So our first method is we're doing a belly landing. So we move the door back on the fuselage, and we're either going to use electromagnets, an Arduino, or a spring held with a pin in order to release that door when we're over the village. Our second method is to use a sushi mat sort of structure with a motor on each end that will open and close the hatch in order to deploy it over the village. And the two-motor method was chosen in order to not clog up the opening, but this will decrease the need to have an opening hatch that will cause drag during the mission. Our third method would be an actuator that would kick it out of the back of the aircraft in order to even decrease the drag that would cause from an opening on the bottom of the fuselage. And our last idea that we have so far is to use similar to what the Tesla structure is, in that it'll have hinges on the side and just open up the bottom of the fuselage to deploy the payload.
So to narrow down our concept ideas, we created 10 weighted decision matrices, and each member of the team filled out their own decision matrix. And from those, we narrowed it down to 2 primary options, which you can see here made in OpenVSP. From these 2 options, we then had discussions among the team and with our advisor regarding which option we decided to go with, and we ended up choosing the option on the left. So from there, we've created a preliminary 3DE model. Internal components are not yet modeled because they're not finalized yet, but we wanted to start gaining experience in modeling using 3DE so that when we know those parts, we're able to construct them. So to size our aircraft, we used the constraint sizing spreadsheets provided to us. Some assumptions included a parasitic drag coefficient of 0.03, as we don't have landing gear, so we think that'll be rather low. We chose efficiencies around the middle of the range provided to us, such as a span efficiency of 0.8, propeller efficiency of 0.6, and motor efficiencies of 0.75. Our CLmax came from our airfoil, and a throw velocity of 20 feet per second was chosen as it's on the lower range of the suggested range. From there, we have a constraint chart where we chose our component. So our 2 main constraints are hand launching and stalling, which are given by the blue and green lines respectively. So from there, we chose a power loading of 66 watts per pound and 1.25 pounds per feet squared. In addition, we also checked if those efficiencies were lower, even at the lowest range suggested, and we found that this did not change any of our major constraints enough to validate changing that point. So using those 2 values, we did weight sizing. We knew that our cruise had to be 12.4 miles for the farthest village of all the villages that we're looking at. So we are designing around that point, and we are loitering for 0.1 hour as we drop our payload. And both of those are at 27 miles per hour, as we found that that was the most efficient speed to fly it. Our payload weight is 4.27 pounds, which includes not only the payload that we're going to drop, but also the computers and flight stuff that we need to carry as well. So from there, we did a trade study with different empty weight fractions to determine the total weight of our aircraft, and we decided to settle on an empty weight fraction of about 0.55, which will give us a total aircraft weight of 12 pounds. With that empty weight fraction, we get a payload weight of about 4.3 pounds, a battery weight of about 1.1 pound, and an empty weight of about 6.6 pounds, which includes structure and propulsion.
On to our VN diagram, using the density on top of the Haitian mountain and cruising speeds of 25 to 30 miles per hour, we found our load factor approached 1.7 on the higher end. Our maneuvering speed load factors only need to be in between 1 to 1.5, but we accounted for this higher factor to make sure we could achieve full cruise. We see that all speed at 1G is calculated and shown on the graph to be 20 miles per hour. So our speeds from there, maneuvering speed A is greater than this at 23 miles per hour, cruise is 27, and ultimately dive speed is 38 miles per hour. We then need to calculate Reynolds number based off of density, speed, chord, and air viscosity, and these will be used later on for airfoil analysis. As far as aeroelastic and banking effects are concerned, they play a small role due to our straight line delivery. When accounting for gusts, we use the speeds of 25 to 50 feet per second, and we display the worst case scenario on the graph. They will not play a large role, and we can still continue our mission within the flight envelope. Moving on to stability, our systems engineering list gave us a total weight of approximately 12 pounds. We then needed to find our center of gravity. The center of gravity using the equation shown is the summation of individual masses times their lever arm divided by the total mass. With and without the payload, this came out to be 37% of the length of the craft, or in better terms, 2¼ feet. To account for mass uncertainty and mass variation, we placed a ballast mass at the nose of our craft to make sure our CG settles where we want it to be. When we reduce the CG to a percent of the mean aerodynamic chord, we're able to find the neutral point and static margin. The static margin equation shown is the percent neutral point minus the percent CG. This value needs to be positive and between 5 to 15% for acceptable flight conditions. We can now move on to our diagram. As we see here, we have rectangular wings with no sweep. We relied on an RC calculator and MATLAB formulas to determine our neutral point. Shown is the coordinate system based off of the nose, but when we did our calculations, it was converted from the leading edge. Common neutral points are typically around 40% of the mean aerodynamic chord, and ours satisfies this condition by being at 39%. And in terms of the mean aerodynamic chord, the CG is at 3.87 inches, or 30% of the MAC. So subtracting the two numbers, we find our static margin is now 9%, which is within the acceptable range and close to the desired margin of 10%. Also, we see without any payload, the CG does not shift in location, so no new moment is created, and thus no control variation is necessary. As a sanity check, we wanted to make sure that that the static margin was 0 when CG equaled the neutral point to make sure our calculations were accurate. Moving on to airfoils, we used X-Flyer 5 to look at these 5 airfoils. The 3 on the left are for the main wing, and the 2 on the right are for the tail selection. For the main wing, we have a conventional airfoil, a high-lift airfoil, and a moderate shape, and then the tail selections were both symmetric. Looking at main wing airfoils more in depth, the first we looked at was the NACA 2412, which is a conventional high-performance, not high-performance, but strong stability airfoil, and it does not provide enough lift for our desired performance levels. The S1223 is a low Reynolds number high-lift airfoil common for RC planes. It has the highest lift coefficient, but only a moderate L/D efficiency, and the manufacturing for this airfoil would be a large headache due to its high camberedness. Ultimately, we decided to go with the DAE 31 for our main wing airfoil, as it meets all of the required lift, L/D, and camber with less of a headache for manufacturing. Moving on to the tail airfoil selection, we wanted these to be symmetric, so that no new lifting moment needed to be accounted for. The 2 candidates we selected were the 0010 and the 0012. As the name suggests, the 0010 has a max thickness to chord ratio of 10%, so it is thinner but also has less performance. And then the 0012 is thicker at 12%, has higher performance, and this should aid in the negative lifting moment for our main wing. The thicker the airfoil it is, the easier it is to manufacture, and both have 0 lift at 0 degrees angle of attack, so we decided to use the 0012 as our tail airfoil. We can finally move into moment coefficient analysis. We see that the DAE is neutrally stable within the 6 degrees angle of attack used. The 0012 will provide strong stability as it has negative slope underneath the 6 degrees angle of attack used. Riley will now discuss the full plane analysis in X-Flyer 5.
So we got a lot of numbers off of MATLAB scripts and the constraint sizing spreadsheet, but we wanted to do another analysis next flyer with the full airplane just to make sure that the numbers that we were getting were actually within the realm of sanity. So what we did is we created the geometry in XFlyer 5, and then, can I get next slide? And then ran analysis to get lift curves and drag pullers for the entire airplane as a whole, so including the tail and the wing. And you can see that our slope of CLO versus alpha is a little bit lower, which is to be expected, and then we don't quite get the same 1.6 lift coefficient. It goes up to just over 1 before we hit stall. And then the CL over CD is occurring at an angle of attack of about 3. And next slide. But this is the really interesting part, is that we were getting our max L over D at around our cruise speed. So that was nice to confirm that what we'd chosen as our cruise speed was actually the max CL over CD, and then our stall speed was again around 20 miles per hour, which is what we predicted. That's a little bit high. It's faster than the average human can sprint, but if we can throw it at 13.5 meters per second with our expected power loading, that means that we should be able to take off with the velocity gained as it falls.
The main goal when sizing our tail was to ensure aircraft stability and control in flight. The neutral point location is primarily controlled by the horizontal tail and its distance from the center of gravity. By calculating the horizontal tail volume coefficient, which is a function of the horizontal tail area, moment arm, wing area, and wing chord, we can check if our horizontal tail volume coefficient falls within the range of a typical well-behaved aircraft. In this case, the range is 0.3 to 0.6, with the value for our UAV coming out to 0.37. This process was then repeated for the vertical tail, with the vertical tail volume coefficient coming out to 0.04, which is again within the typical well-behaved aircraft range of 0.02 to 0.05. With both the coefficients coming out within the specified ranges, our UAV should exhibit adequate pitch behavior, resistance to gusts and other upsets, and yaw dampening and stability. Sizing our control surfaces was done by looking at other aircraft and their typical values, as well as guidelines for RC aircraft design. The rudder will entail 30% of the vertical stabilizer's chord and have a max deflection of 25 degrees. Additionally, it was calculated based on our motor thrust that in the case of one of our motors failing, the rudders can deflect to 16.4 degrees to compensate and continue flying straight. The ailerons have been sized much smaller than the flaps because our mission does not entail much turning or maneuverability, while the larger flaps will help produce more lift on takeoff and can be deflected highly to shorten landings.
All right, good morning. So for our propulsion system, we use MotorCalc to help us make our preliminary selections. Our configuration specifications and performance specifications served as our inputs into the MotorCalc software. And MotorCalc used that information to run trade studies and presented this propulsion system on the left-hand side of this slide as one of its top recommendations. As you can see, using this propulsion system, if we fly at 80% throttle, we can fly at 27 miles an hour for about 34 minutes and 20 seconds. And here you can see our propeller efficiency and thrust compared to our airspeed. And so at 27 miles an hour, we get propeller efficiency of 42% and thrust of 43 ounces. Of course, this is our preliminary propulsion system, so MotorCalc will continue to be used to run trade studies to help us validate and verify that this is the best propulsion system.
We are happy to say that we are on schedule according to what we had originally planned, and following this presentation, we'll be moving into Phase C, which mostly consists of finalizing our designs and beginning our early testing. And our budget has also remained fairly consistent. We have added a few things since last presentation, but it's pretty straightforward and well divided still. And our risk analysis, we have pinpointed our potential concerns and our most likely failure points, and we have brainstormed some risk mitigation for our potential failures, but we feel comfortable moving forward that we will be able to mitigate these risks. And this is our design moving forward. A few basic dimensions and our airfoils and our motor are on this slide, as you can see. Do you have any questions for us?
Hi, Bronco Luckett here. Can you hear me well?
Yes, we can hear you.
I gotta stop asking those questions. So what I'm reading is that your critical requirements are amount of your payload, the fact that you can deploy the payload, and obviously the range. I didn't quite get whether the range includes back and forth flight. I would assume you would need to fly over to the village, deploy the payload, and then fly back and land it at the base. So, you know, the range is obviously an issue, and I'm a little concerned that if you go with a two-motor design, the battery drain, I know there can be two smaller motors, but you know, I'm speculating that the battery life with two motors and more moving parts may not be as efficient as a single motor. Considering the fact that you are deploying your payload, this would be an easy configuration where you can have a single larger diameter efficient propeller in the nose, and then have the batteries in the aft end of the fuselage and have your payload located close to the CG. So when you deploy it, you don't really affect much the balance of the airplane. I'm kind of okay with the two boom tails configuration. What you may want to consider is to have if you have an upside down V tail shape, which I think it's more weight efficient than having two verticals and a horizontal tail, because the junctions and everything may be a little bit more heavy than if you just do a upside down V tail configuration. And then talking about the payload deployment, I hear that you are considering different way of you know, either it's going to be a hatch or payload actuator. You know, in my mind, I don't think that would add any value to overcomplicate the load deployment. I think a simple latch, which can be triggered by a servo and drop of that from the open cavity in the fuselage will absolutely do the job and will reduce the risk of, say, latches failing to open and mission not accomplished, or any additional weight for any specific actuators. Now, you may think that if you have an open hole in the fuselage, you know, that may compromise the belly landing, but I believe that, you know, if you add two skids that are slightly lower than the opening, it can be sufficiently efficient for belly landing. I would not complicate the design of payload deployment. As I said, I would keep it very simple, just a simple latch, drop it off on the fuselage. The fuselage can stay open at such a low speed flight that I don't think aerodynamics will be jeopardized. These are my inputs.
Okay, so I'll respond to a couple of those. In regards to our range, we have considered that as a there and back range, so a round trip. So the longest village is actually 12.4 miles divided by 2 away. So that is a round trip range. And then in regards to the two propellers, the reason we had a couple reasons of going with that. We did know that it's not going to be necessarily as efficient as a single propeller. Our reasons for going for that include that we didn't want to have propellers on the back side of the plane as we're dropping a fuselage or dropping a payload, and we don't want to have any intersection between the propellers and the payload as it's dropped. And then we didn't discuss it as much in this presentation, but we were planning on having a live video feed for the operator of the UAV. and we were planning on putting that in the nose so that we didn't want to have the video go pointing towards the propeller, as it'd be harder to see. So we instead decided to put them attached to the two tail booms as a helping structure, and that ended up giving us two propellers. We were concerned about getting those two propellers in sync, so that's something that we're going to work on as we move forward. As for the payload, we definitely do plan on making the simplest options. Those were just a couple of our early ideas and backup ideas. So, any other comments or questions?
We've got a couple minutes, if you've got a question or comment, or would like to write that down and get that to the team. Okay. Well, with that, we will shift over to the next team here. That is team number 6.